Hello and welcome to all in another one of our lectures in our lecture series on design of structural steel connections. Today we will be looking at a numerical example in which we will perform the calculation of weld stresses. So for the numerical example, as you can see on your screen, we have taken a beam to column connection. This red component is our column, whereas the blue component is our beam, and this beam is being connected to this column through the use of weld. So where are the weld being used? One is here, so let us call this weld group 1. This weld group 1 is connecting the flanges of our beam to the flanges of our column, and let us call this as weld group 2. This weld group 2 is connecting the bottom flange again to the flange of the column. So if you look at the side view of this diagram, you can see where the weld is being placed here. This green color represents the weld that is connecting the beam to our column here. So both beam and column we are using here are a welded I section. For column, let us suppose that the component that we are using or the sizes that we are using is a 415 by 6 mm size wave and 150 by 17 mm size flanges. So if you look at the dimension, this represents a ISMB 450 section column, whereas for beam, let us suppose that the beam that we are using is composed of 368 by 6 mm size wave, and the flanges are 140 by 16 mm flanges. And for the calculation, let us suppose that the load that is coming onto this beam column connection is a shear, which is a downward shear of 50 kilonewton, and also a clockwise moment of 50 kilonewton meter. So let us suppose that these two forces are acting at the connection of our beam and column. Now let us proceed with the calculation of stresses. So before beginning with the calculation of stresses, let us assume that the material that we are using has a yield stress of, okay, let us say which yield stress we will be going to use. Okay, let us suppose that the yield stress of the material of this beam, column and weld is 350 Newton per mm square, so that the ultimate stress is 490 Newton per millimeter squared. So let us suppose these are the grade of the material that we will be using. So to begin with the calculation, let us first assume a size of our weld. Let us say that the size of weld that we have adopted is a weld of 6 mm. So from this size we can calculate throat thickness of the weld. This throat thickness is given by the value 0.7 times S. So 0.7 times the size of weld gives us 4.2 mm. And finally we can calculate the length of weld available. So how we will calculate the length of weld? You can see that the weld is connecting our flanges of our beam to the flanges of our column. So the length of the weld that is available will be this length here. For both weld group 1 and weld group 2, the length of the weld is same, and this length of the weld is equal to the width of the flange. So what is the width of the flange that we are adopting here? 140 mm. So the length of our weld available will also be equal to 140 mm. So these are the parameters that we have considered. So before proceeding with calculation, let us see what kind of stresses do these shear forces and these moments create. In our last class, we discussed about F and Q stresses. So if the stresses are perpendicular to the weld length or weld run. If the stresses are perpendicular to the weld length, we call those stresses as F stresses, and if the stresses are parallel to the weld length, we call these stresses as Q stresses. So first, for the case of this shear force, you can see that the shear force is acting vertically downward here, and our weld length or the length of the weld is perpendicular to the plane of the screen. That means it is just going through this screen, if you can visualize. So the shear force that is acting in the vertically downward direction will also create stresses in the downward direction. If you draw those stresses, you can draw in this way here in the side view. So we can see that the stresses created by these shear forces will be perpendicular to the length of the weld. So that what we can say is the shear force creates F stresses. Similarly, in the case of this moment that we have a moment of 50 kilonewton meter, we can resolve this moment into a tension compression couple. So this tension that is acting in the upper flanges of the beam, and this compression that is acting in the lower flange of the beam. And the distance between this tension compression couple we can represent as capital H, which is known as lever arm. So resolving this moment into tension and compression forces, we can see that the tension forces will create stresses in the same direction. And again, this direction will be perpendicular to the length of the weld, because the length of the weld is perpendicular to the plane of the screen, and the tension forces are creating stresses in this direction. So both moment and the shear forces in this case are creating F stresses. So after knowing this, now let us go to calculating the stresses or the forces due to shear force and moment individually. So first, let's start with the stress due to shear force. So due to shear force, we have a total shear force of 50 kilonewton. Let us say that each weld group is, both weld group 1 and weld group 2 is resisting equal amount of shear force, that is half of 50 kilonewton, which will be given by 25 kilonewton. So if you are using any finite element software to calculate the shear forces that is resisting, that the weld is resisting, then it may not be equal as we have assumed now. But for now we will just assume that each weld group is resisting half of the shear force, that will be 25 kilonewton. So what will be the stress in weld group 1 due to shear force? You can say either weld group 1 or weld group 2. Let us represent it as F1, because the shear force is creating F stresses, and we will represent this as F1. So this will be given by, as we have seen, the value of force divided by throat thickness into length of weld. We have discussed about this formula. So the value of the force will be 25 kilonewton. The throat thickness will be 4.2 mm, and the length of the weld will be 140 mm. So if you perform this calculation and you change the value to Newton per millimeter square, then you will get the stress to be 42.517 Newton per millimeter square. So this is the F stress that is acting on our connection, or that is acting on our weld group, individual weld group, due to the shear force. Now let us go to calculating the stresses due to moment. So you can see that this is the formula to calculate the stresses, and to calculate the stresses we have to calculate the force. So what will be this force due to moment? In case of shear we can directly use this force value, but due to moment we do not have the force value, rather we have the 50 kilonewton value moment only. So how to calculate the force here? So the general formula is the value of the tension force multiplied with the value of the lever arm H, or you can also write this as the value of the compressive force into the value of the lever arm, either this or this. This will give you the value of moment. Now since we are considering a tension compression couple, the value of this tension force or the compression force will be the same. So either multiplying the tension force or the compression force with the lever arm will give you the value of the moment. So what will be the value of the lever arm here? We know that the flange section of the beam is 140 by 16 mm. And the wave is 368 by 6 mm. So the total lever arm will be given by the depth of this wave, which is 368 mm, plus 2 times the thickness of these flanges. We know the thickness of the flanges is 16 mm, so 2 into 16 mm. This means 368 plus 32 mm. So this will give you the value of lever arm is 400 mm. So why are adopting this overall depth for the calculation of lever arm? Because if you remember your strength of material classes, we know that for this I section beam, the bending stresses will be distributed in this way. So here will be the tension forces and here will be the compression forces. And we know that the maximum bending stress is resisted by the weld at this level and at this level. And also because our weld are present at the end level or the extreme level of this bending stress diagram, so we are calculating the overall depth for the calculation of lever arm. So now we have calculated the overall depth or the lever arm. The value of tension or the compression force will be given by M over H. So M we have 50 kilonewton meter and the H we have 400 mm. So if you perform this calculation, you will get the value of tension or compression force to be 125 kilonewton. Now again we have to calculate the stress in weld group 1 or weld group 2, and we will represent this by F2 for now. Now the force is 125 kilonewton divided by throat thickness is 4.2 mm into the length of the weld will be the same, 140 mm. So this calculation will give you a stress of 212.585 Newton per millimeter square. So now we have calculated the stresses individually due to the shear force and due to the moment also. Now next step is to calculate the equivalent stress. So we have the formula for equivalent stress to be equal to, as we discussed and as given in our code, F square plus 3Q square whole under root. So we don't have Q stresses for now. This will tend to 0 and the equivalent stress will be now found out by F1 square plus F2 square. So F1 we have 42.517 square plus F2 you have 212.585 square. You get the value of equivalent stress to be 216.795 Newton per millimeter square. So this is the equivalent stress acting in each weld, in this both weld group 1 and weld group 2 also. Now before finalizing the solution, we have to calculate whether this equivalent stress is less than or equal to the permissible design stress. To do that, we will calculate the permissible design stress or the permissible weld stress by the formula Fu over root 3 gamma mw. So the Fu value we have 490 Newton per millimeter square root 3 into the partial safety factor for shop welding will be 1.25. So you will get the value to be 226 Newton per millimeter square. So if you compare the permissible value of the stress and the actual value of the stress, you can see that the permissible value of the stress is greater than the equivalent stress that is acting on our weld. So the design of this weld is okay. And remember, not only the equivalent stress that we have calculated is the final. If we have, suppose we have a condition in which the stresses acting in the weld are both F stress and Q stress, and using this F and Q stress we calculate the equivalent stress to be F square plus 3Q square. So not only this equivalent stress should be less than FWD or the design stress, these two stresses F and Q stress should also individually be less than the design stress. We have to check for that condition also. So both, or let us say all these values, F value, Q value and FE value, each should be individually at least less than or equal to the design stress in the weld FWD. So in our case, this 226 is greater than the equivalent stress, so the design or the calculation of the weld stresses is within the permissible limits. So this is how you calculate the weld stresses. We saw an example for a very simple case in which an I-beam is being connected to an I-section column with weld, and those welds are only connecting the beam flanges to the column flanges. There is no weld that is connecting the wave of our beam to the flanges of our column. So we will end our lecture for today, and in our next lecture, this same example we will once look in Idea Statica software and see the result that may be derived from those software analysis, and we will compare those results with our manual calculation results. So till then, keep watching our YouTube channel. Thank you.